Hey, how you doing, everybody? All right, it is Monday, and we had a problem with Rock Connect and logging in, and Zoom and Amazon Web Services seem to be failing nationwide. So, oh wait, I need this over here. That'll be handy. Okay, so yes, we had some issues. We had some issues, and let me move that over there. There we go. There we go. That's better. Move it. So we had some issues, and so I thought I would give you a video on how to get this done. Right. This is a copy of 8 lesson 5 displaying and describing categorical data. And so that's the name of the game today: displaying and describing categorical data. Here we go. Well, what happened on the Titanic at 11:40 on the night of April 14th, 1912 is well known. Frederick Fleet's cry of "Iceberg right ahead!" and the 3 accompanying pulls of the crow's nest bell signaled the beginning of a nightmare that has become legend. By 2:15 a.m., the Titanic, thought by many to be unsinkable, had sunk, leaving more than 1,500 passengers and crew members on board to meet their icy fate. Here is some data about passengers and crew about the Titanic. Um, each case row of the data table represents a person on board the ship. The variables are the person's survival status, dead or alive, age, adult or child, and sex, male or female, and the ticket class, first class, second class, third class, or crew. So here's a little sample of this data table. So we've got this person who died. They were an adult, they were male, and they were in third class. This person died. They were adult, they were male, they were part of the crew. This person died. They were adult, they were male, they were part of third class, and so on. We have one person that was alive, adult, female, and first class. Okay, so the problem with a data table like this, in fact, the problem with all data tables, is that it's a little bit hard to see what's going on. And the whole purpose of organizing the data is so that we can quickly ascertain and see what it is that the data is trying to tell us. Right? We need other ways to show the data so that we can see the patterns, we can see the relationships, we can see the trends and exceptions. So there are 3 rules of data analysis. Remember, statistics is all about the organization and analysis of data. 3 rules of data analysis. What should we do with data like this? There are 3 things that we should always do first with data. We should make a picture, make a picture, make a picture. We should make a picture and display our data that reveal things that we're not likely to see in a table of numbers, and will help us think clearly about the patterns and relationships that may be hiding in the data. We want to make a picture, a well-designed display that will show the important features and patterns in our data. A picture will also show us all the things that we did not expect to see, the extraordinary and possibly wrong data values or unexpected patterns. And we want to make a picture to tell. The best way to tell others about our data is with a well-chosen picture. So, to make a picture of data, the first thing we'll need to have to do is make piles. Right? Making a pile is the beginning of understanding about data. We pile together things that seem to go together, and so we see how the cases distribute among different categories. So for categorical data, piling can be kind of easy. We count the number of cases corresponding to each category and pile them up. One way is to put 2,201 people. 2,201 people on the Titanic into piles is by ticket class, counting up how many had each kind of ticket, and we can organize these counts into a frequency table, which records the totals and the category names. So even when we have thousands of cases, a variable like ticket class with only a few categories and has a frequency table that's easy to read. So for instance, here we go. There's our count. We had 325 people who had first class tickets. We had 285 people with second class tickets, 706 people with third class tickets, and 885 crew members with tickets. So let's complete this data table. And oh, that's very nice. We've got a something in here. Hopefully I can type in here. No? Can I? I have to draw. Interesting. I don't know if I want to draw. I need to be seeing this in order to do the drawing. So this is why I don't know if I want to. Can I move this over? Okay. As long as I can see. No, I need you to move over there. Drawing. There we go. Then I don't mind. If I can do that, I don't mind. You guys might mind because you might not have fancy drawing tools like I have. Okay. Fancy drawing tools that are cluttered. Oh, no. No. Look at that. The moment I pick up this pad, okay. That was the last thing I wanted you to do, computer. The last thing. Okay. So a line. What kind of line do I want? I want to be able to do a squiggle. I want to scribble. Okay. So the first thing I need to do is I need a total here, right? I need to know what. Okay, if it's not going to draw, then what? I don't understand. Scribble. Me. Scribble. So I draw on it, and yet it does not what I want. So let me try a text box. Maybe it'll behave if I ask it to do a text box. Okay, it's behaving now. I'll deal with this. 285 plus 706. I need a total. Why do I need a total? Because what I'm being asked to do over here is I'm being asked to find a percentage behind here, which is now being hidden. Yeah, come on, Google. Why aren't you smarter? Well, you see that percentage sign right there? You see that percentage sign? That tells me that it wants me to find a percentage. And if it wants a percentage, I need a oopsie daisy, I didn't want that. If I want a percentage, I need a total, right? Because a percentage is kind of a reflection of what this reflects out of 100, right? So I'm going to grab my own physical calculator over here and not even try to pull up the electronic calculator at the moment. 325 plus 285 plus 706 plus 885. All right, I get a total of 2,201. Oh, I should have known that, right? The question said something about 2,201. That number sounds familiar. So if I want a percentage of each one, here's the first class percentage, right? It's going to be 325 divided by 2,201, times 100. Now, ordinarily, I would say good, mathematical hygiene is to put that in parentheses because that way, it forces everything to happen the way you want it to happen, right? I want this calculation to happen first. 285 divided by 2,201. I want this to happen first, which is why it gets parentheses, and then I want it to multiply by 100 to get that percentage. But the thing is you don't need it in this particular case. You don't need that good hygiene because in this case, we're just combining just division and multiplication together, which makes everything a little bit less complicated. There's no PEMDAS rules we're going to be violating or anything. So 706 divided by 2,201 times 100 equals, and then crew percentage. All right, we got 885 crew members divided by a total of 2,201 total people. Again, math hygiene tells me I want to put some parentheses in here. You don't need them in this case, but I like to teach it this way so that when we do have more complicated stuff, you're not confused, okay? All right, I think I'm done. I think I got everything. I'm just checking my numbers over. Now I'm going to do some computation with my physical calculator here, right? I got 325 divided by 2,001, 2,201, and then times that by 100. And this is about 14. To say round to the nearest something or other. Ms. Desiato is usually really good about giving us those instructions. I don't know, so I'm going to take it out to the nearest thousandth, and just in case. 0.766. All right. And then the next one, 285 divided by 2,201 times 100 is 12.949. I round to the nearest thousandth. 706 divided by 2,201 times 100 is 32.076 percent. And then last but not least, 885 divided by 2,201 times 100 equals 40.2200210. Because that, oh wait, no, I was wrong. 209 around. Okay, so that's what I got. I got some percentages. And so let me save and close. Let me see if I can get this to go in there. What in the heck? Did I like totally not have to do this? Because I feel like before I put my drawing in, I didn't see this stuff. I didn't see this whole area. Maybe this is a trick of the mind. But I basically just calculated what's in this table, and I probably didn't need to do that now that it's popped back up. I thought this was. I'm going to check the video after I get done with this because I thought this was blank. I didn't see any numbers here. Maybe this was used to block. Maybe Ms. Desiato didn't want you to see or something, and she put this drawing here so you wouldn't see it at first. And then once I wrote on it, it made it transparent, and so now it's not doing the thing. So I feel silly. Okay. But anyway, yeah, here's the percentages, right? And so you look at the numbers and you can kind of get an idea of the relative proportions of these numbers, but it's not until you put them in percentages that you can make more sense of them, right? The percentages make more sense of this, right? I don't get a sense of what percentage of the crew is 885 until I divide that by the total and I figure this out to be what it is, right? So, bar charts. Here's another picture, right? So this is one picture we can draw of the data. This helps. Bar charts is another kind of picture. Let's look at the bar chart on the right. The height of each bar shows the count for its category. The bars are the same widths, so the height counts. So their heights are the counts in each class, right? There's the first class count, there's the second class count, the third class count, and the crew count. So if we had a question like, can we say that the majority of people were crew members? Explain. So I look at this and I say, were the majority crew members? Well, the most frequent category is the crew, right? Crew, there's more crew than there are third and there are second and first. But there's not a majority crew. I can kind of see that because if I take second class with third, I can see that second class plus third is more than the crew. So that's before I even add first class. So definitely crew is not the majority, but they're not 50% or more, but they're close. And if I see by the percentage, it's like 40%, right? Slightly less than half of the people on board were crew. So the answer is, now that it's easy to see the majority of people on board were not crew, we can also see that there are about 3 times as many crew as second class passengers, and there were more than twice as many third class passengers as either first or second class passengers, something we might have missed just looking at the frequency table. The bar chart displays the distribution of a categorical variable, showing the counts for each category next to each other for easy comparison. And our third picture here is pie charts. Another common display that shows how a whole group breaks into several categories is a pie chart. A pie chart shows the whole group of cases as a circle. And then they slice the circle into pieces whose sizes are proportional to that fraction of the whole in the category, right? So the crew is 40%. Look how this slice is nearly half this pie or this pizza or this circle, right? This is 40. This is a 40% slice. So which category had the most passengers? Well, that's crew, right? Crew had the most passengers. Were there more crew? Were there more crew or more third-class passengers? I can easily see there were more crew members than third-class passengers. And I gotta make these bold so you know that I wrote them in. right? So, a statistics class reports the following data on sex and eye color for students in the class. What percent of females are brown-eyed? Okay, so what percent of females are brown-eyed? Well, we did some practice on this. I'm going to give you a chance to answer all of these. So here's what I recommend. I recommend you give each one of these a shot. It might take you a minute or less to do each one of these, so about 5 minutes to complete these 5 questions. Pause this video now and don't watch me do it, because I know even if you feel like you're pretty good at this by now, you're going to want the practice, just because you want to get so good at this that it becomes automatic. You don't want to have to think about all these things. You want to leave your mind as much as your mental capacity available for bigger thoughts, all right, than just this stuff. So pause me now and give this a try. All right, great. You paused me. I shut up for a minute. You got to hear your own thoughts. Let me do these, and we'll just go over it, right? What percent of females are brown-eyed? Okay, so females that are brown-eyed. So here's the females. There's the brown-eyed females. There's 16. So it asks, what percent of females are brown-eyed? And percent equals part divided by whole times 100. All right, that's what percent is. So what do I got here? I've got part is 16, right? That's the females that are brown-eyed. All right, and then what's my whole? Is my whole 64 out of all? Does it say of all people, what percent are brown-eyed females? No, it says what percent of females. What percent of females? So I don't want to compare it to 64. I want to compare it to 32. So 16 out of 32 times 100 are brown-eyed females, right? And I probably don't even need a calculator for this. I can see that that's going to be 50%. I know that 16 is half of 32. If you need a calculator for that, that's fine. That's no biggie. 50%, right? 50% of females here are going to be brown-eyed. The next question is, what percent of brown-eyed students are female? What percent of brown-eyed students are female? So what percent of brown-eyed students? So what's my part? Right? My part is brown-eyed students. Brown-eyed students, there's 36 brown-eyed students. You see that? Brown, color, eye color, brown, 36 total students. 36 is my part. That's my part. What's my whole? My whole. What percent of brown-eyed students are female? Oh, wait, I read this wrong. What percent of brown-eyed students are female? So brown-eyed students is actually my whole, right? And then what percentage of them are female? 16, right? 16 out of 36. 16 is the number of female brown-eyed students of all brown-eyed students, right? What percent of all brown-eyed students are female? Female is our part, that's 16, and 36 is our whole. Okay, there we go. So I know this is 50% too, right? I can just look at it and say, oh yeah, I know that. 16 is, no, wait, no, it's not. No, Mr. Salt. Hopefully someone corrected me on that one. No, 16 is not half. 32 is half. It's double 16. So 16 divided by 36 is going to be a little different. It's going to be 44 repeating, right? So does it say what to round to? I got nothing about what to round to. We'll call it 44.4%, or round to the nearest tenth. 44.4%. We'll round to the nearest tenth there. That's the percent of brown-eyed students that are female, right? Percent of brown-eyed students that are female. Brown-eyed students that are female. All right. Next one. What percent of brown-eyed students, what percent of students are brown-eyed females? Woo! You got to read these real carefully, as you can tell. Even I need to read these very carefully. What percent of students are brown-eyed females? So of students tells me that my whole is going to be of students, which is students as a whole, right? That's my big number. That's my 64. So I've got something divided by 64. It's going to, and then times that by 100. It's going to give me the percent. What's the part? What percent of students are brown-eyed females? Okay, brown-eyed females is definitely my part. My part is 16. So I got 16 divided by 64. Isn't that 1/4? 16 divided by 64. Yes, that's 1/4. Or 25%. 25%, right? My part, 16 brown-eyed females divided by the whole of 64 total students times 100. Compare the percent who are female among blue-eyed students. Woo! The percent of who are female among blue-eyed students to the percent of all students who are female. Hot diggity darn! This is a that is a tongue twister of percentages. Let's do it. Let's do it. I'm going to shrink this a little bit and take up a little less space. Fit some more on the page. Okay, we got two. We're comparing two percentages now. Comparing two percentages now, right? The one is I have a percent which is going to be equal to. All right, ready? The percent who are female. Percent who are female among blue-eyed students. Among blue-eyed students. So the percent who are female, that's my part. Among the blue-eyed students, that's my whole. So I'm looking at blue-eyed students. There's 10 blue-eyed students. I believe that's my whole. The percent of those who are female, there's 4 female blue-eyed students. So of blue-eyed students, how many of them, of blue-eyed students, how many of them are female? 40%. 40%. All right, oh, now times 100, and the 40% goes over here, Mr. Salt. All right, now I got to compare this among blue-eyed students. Oh, I compare this to the percent of all students who are female. Of all students who are female. So all students, that's definitely going to be my whole, right? All students. I got. Why did I do that? I'm like all of a sudden the font got really weird, and I'm like, why is it doing this to me? Okay, fine. Yeah. There we go. And then bold. And then maybe a little bigger. There we go. Okay. What was I doing? Oh, yeah. To the percent of all students that are female. So that all students is 64. That's our whole. Of all students, how many are female? That's 32. 32 out of the 64. Oh, that's 50%, right? Times 100. Not 1,000. It's 50%. 50%. Okay, now it asked me to compare, so I probably need like a sentence here, right? I need a sentence. There is a greater percentage of students who are female than there are females, as there are females among blue-eyed. Oh, why did they go over there? Blue-eyed. Among blue-eyed students. All right, there's a greater percentage of students who are female than there are females among blue-eyed students. Comparing two percentages, right? Percentage of students that are female is 50%. The percentage of females that are blue-eyed of blue-eyed students is 40%. So there's a greater percentage of students that are female than, yeah. Okay, I think we've got that, right? Hopefully. Number 5 asks an even more difficult question. Does it seem that eye color and sex are independent? Now, we have not talked about independence before. Independence means, is one thing seem to be related to the other? Is one thing causing the other? Is there some pattern that's developing? or is this a completely random association? If these things are independent, then there should be pretty much a random distribution between these two pieces of data. If these things are dependent on each other, then something's going on where something's causing a non-random distribution, right? These things are somehow predictive of each other, right? If things are dependent on each other, then they become predictive. They begin to be give you a probability of prediction. So so I should look for pretty much random distribution. And the difference between 6 and 4 is not so much that in a small data set like this, that's not too big. That's not too much of a difference of a distribution. I wonder even about this, even though there's a difference of 4 here, with a small data set, this could easily be explained by just random things. But this one over here concerns me, not because the difference is 6, but because the proportion is almost double the amount of females that have green, hazel, or other eyes than males. So I suddenly begin to wonder, is there something going on here? So I would, if it was me, I would say we can't be sure that eye color. Sorry, I'm going to have trouble speaking to you while typing a sentence at the same time. I just don't have that much excess processing memory. We can't be sure that eye color and sex are independent with such a small data set, right? This data set is kind of small, but there might be a connection between gender and, see, green, hazel, other. Green, hazel, other. It just seems like there is a significant enough difference there that it might not be random, right? It might not be random that there's double the amount of females that have green, hazel, other. Whereas it seems like it could be random. But this obviously could be random. I mean, the data set's so darn small, it's really hard to say. We could run some tests, but our confidence level would be so low. Let's keep it honest. So here's a pie chart that displays the data percentage of high school students who engage in specified dangerous behaviors as reported by the Centers for Disease Control. So we have marijuana, heavy drinking, use alcohol. What's wrong with this plot? What don't you like about this? Maybe pause the video, give it 60 seconds to think about. What could possibly be wrong with using a pie chart to display this data? Great. You unpaused me, and you gave it 60 seconds of thought. Well, as I look at it, I'm like, they're heavy drinking versus use alcohol and marijuana. But couldn't someone use alcohol and smoke marijuana? Like, that's possible, right? Couldn't someone be all of these? It's not like these are really good defined categories that you'd only be in one or the other of these. There's a little bit of categorical definitional bleed going on here, where the categories are kind of fuzzy-ish, and the categories are fuzzy or fuzzily defined, and I wouldn't. This isn't the picture I would choose to display this data. All right. Let's see. Overall averages or percentages may be misleading. During an investigation of admission rates for men and women at the University of California at Berkeley's graduate schools, as reported in the article Science, about 45% of male applicants were admitted, but only about 30% of female applicants got in. It looked like a clear case of discrimination. But was there a clear case of discrimination? Maybe talk and think about whether you think there was or not. Maybe pause the video, give it some thought. You tell me. And you know what? I think class is about to start, so I'm going to stop this video here, and I'll just make another one if I can continue on, okay? I'm going to pause here, and hope to see you in class.